So the thing is that Blaze is a library that among other things allows you to avoid that sort of thing. And because I like structuring my presentations, I'm going to try and lay out a few things in advance about what I'm going to talk about. So we'll take a look at what Blaze is, what it can do, why you might be interested, and then dive a little bit into how it works and what other related work to take a look at. So there will be links in these slides, and there's a Jupyter notebook that goes with it. And I will make sure that they are published, so that you guys can enjoy the online resources. So first, I'm just going to let the marketing spiel from the website do a little bit of talking for me for part of this. Blaze presents a pleasant and familiar interface to us, regardless of what computational solution or database we use. In other words, it lets us query the same data across different systems. And you might be thinking, okay, great, so one query works across different systems, but do we really need another DSL? Like, what form does this query take? So fortunately for everyone who is concerned about that, Blaze basically uses the NumPy/pandas data frame syntax, mostly, and translates the operations to whatever makes sense for the underlying data store. Now, talks are no fun without examples. So for the purposes of this talk, we're going to pretend that we're working on an online bookstore that's named after a rainforest. And we have books that are in MongoDB, so we can manage them easily and serve them up fast. We have user profiles and libraries stored in Postgres because we don't want to lose that data, and MongoDB is not so good at that. We have a purchase history data dump in CSV because we're letting someone else handle payments, and we're not crazy. And we have web server logs, which we're getting from Kibana or something. We're accessing it in CSV format. JSON is just as good. I say that in preparing this talk, I discovered a bug in JSON handling in Blaze, so the next version will definitely happen.
How long have you been working on that bug?
Most of this week. So anyway, so now we will look at this data. We're going to load this data into Blaze, do some simple exploratory queries on it. And this is the bit where I open up a Jupyter notebook and start live coding, so things will traditionally go horribly wrong. So, Blaze, exploring some data sets. We like data sets. I'm going to move this very slightly so I can actually see what I'm doing. Cool. Okay, so the first thing we're going to do is import Blaze. Notice it takes a second or two. There's a whole bunch of dependencies that it needs to try and load in. So the first data set we're going to look at is our transaction log, because it's pretty simple. It's a CSV file. And in our fictional world, we get it from our payments processor. So all we do is we say Blaze data. Here's the name of the file. And we can get the first few items there. It's very simple. It looks like a pandas data frame. It behaves in the notebook like a pandas data frame. Okay, so let's do some hardcore data science. Who are the top 5 big spenders in our data set? So we take the transactions, we group them by user ID, we combine the sum of the purchase price for each, and sort the results. Our top 5 big spenders are these user IDs, and as you see, our bookstore is not a very high-spending bookstore. That this guy spent $37, and he's the big spender. Now, we care about our fictional users too, so we store them in their own table in Postgres. So all we need to do for this is pass Blaze a connection string. This is a standard SQL Alchemy connection string, which is what Blaze uses under the hood. And Blaze will take care of everything for us. You'll notice that you've got your standard connection string, and then you've got this colon. Anyone want to guess what that does?
It's a database.
So you've got the database before the colon, and after the colon is the table. Because Blaze is sort of optimized for tabular data. At least Blaze can handle non-tabular data, but it's kind of a pain in the ass to try and query it. So we're looking at the users table, and here are our users. Bear in mind that this user data set is something that I got from the random generator, and randomly assigned some genders too. So let's find out how many men and women are customers of our bookstore. Really simple, group by gender. Oh look, it turns out there's a bunch of people who don't fit into the ridiculous binary system. Well, now we know. Okay, we also store user and book relations in Postgres because why not? And reviewing them is equally simple, so we know who owns what books. So let's find out who has the most books. We join, we group up, and we say, okay, our biggest readers only have 11 books. So this is, this is not the most lucrative or successful of bookstores yet, clearly, but but we're able to see this. And the thing is that you'll notice we've queried 3 different data stores, and the queries have all looked exactly the same, which is really handy. So the thing is, our books, on the other hand, they're stored in MongoDB because JSON documents are a thing, and I want another data store to play with. So this is actually the top 100 books from Project Gutenberg, which I've randomly assigned prices to and put into place. So the thing is that this data set as well illustrates one of the shortcomings of Blaze, which I mentioned briefly, which is that if your data doesn't look like a table, it's kind of a pain in the ass. Blaze is really good with tables. It will infer kind of the shape of your table. It will figure out a lot of stuff for you. But it likes to know the shape of the data, and it's not good at inferring things from non-tables. So if your data is not tabular in shape, you kind of need to tell them. This is what we're doing over here, is we're saying, okay, here's a shape, and we'll go into this in a little bit. We'll see exactly what this is. But here's the shape of our data. We have an ID field, we have an author, a title, categories, and these are strings, or might be strings, or might not be present at all. And we give it a MongoDB connection string. This is Hi Mongo under the hood. You'll notice that we've got the same database : collection name thing going on like we do with SQL Alchemy. And we give it a shape to look for it, and we put it in there and we say, tell us about the books. And it knows a lot about the books. So we actually have all the text here, except for this text about this calculus textbook, because it was kind of hard to find on Project Gutenberg, and I couldn't be bothered. Yeah, also, pro tip, if you're ever trying to scrape Project Gutenberg, don't actually use Project Gutenberg. Use a mirror. There's a great mirror called Reading Rooms. They will let you arbitrarily hit their server. Use that. Anyway, so here are some books. Okay, let's find the average price per author who has multiple books. So we take our books, we group them by author, we get the average price per author. We filter out the average price per author where their number of books is less than or equal to 1. So we're only looking for ones that have multiple books. And we sort them descending, and we get the top 5. So it seems that everyone likes philosophy. Herr Nietzsche is on top of our list. Oscar Wilde is also very popular, as is Franz Kafka, James Joyce, and Anonymous. So
that's you, right?
Don't tell anyone. So last but not least, we have our server logs. And the thing is that these are coming over HTTP from our fictional log aggregator, which, actually I just generated them with a simple script. They're actually stored as a giant JSON blob. And I would be happy to show anyone the really simple Tornado app that actually serves them. But I have this app running on my machine. It's an HTTP URL right here. And I'm asking for the CSV data because that's easy to parse. Failed. Okay. See, I told you something would go horribly wrong. So connection refused. I presume that's because I've completely failed to start the server. So we're going to do that. Yes, it is because I've completely failed to start the server. Well, there you go. Okay, so I started the server process now, and there we go. Okay, let's try this again. So now the server process has started. You will notice that it's going over the HTTP connection. It's very happy to retrieve the data in any format that it understands. It's parsing it, and it's presenting it just like we saw, as a sort of data framey looking thing. Okay, so let's filter out the log entries that don't refer to downloads, because that's all we care about. And there's a bunch of random noise in there. Cool. And let's plot some things. Who likes to see request times in a web app? They're fun, right? Let's plot something. So bouquet has loaded. We're going to try and do this again. As you see, Wesley is very interested in learning more about bouquet. Hooray! Look, it's a plot. You'll notice that we've got kind of weird and spiky requests here. Most everything is clustered down there under 1,000 milliseconds per request, but we've got a lot of weird spikes. So let's find out what's actually up there. Let's find all the requests that are above the 99th percentile. So I need a little help from this web page from Austin University to figure out exactly what the formula needed to be to give me that 99th percentile time. But once I figured that out, I said, okay, well, all of these operations, just like on a pandas data frame or a pandas series, are natively supported by Blaze. So Blaze is very happy to compute them across any backend, including our download logs. So you can get the mean and the standard deviation pretty trivially. And let's filter out all of the, and look at all of the queries where the duration is greater than the 99th percentile duration. Wow, that's so this one in particular, over here, where is it? Yeah, that's a really long query. 3.6 seconds just to download something. That's slow. That's not good. We can also see that some of this sort of seems to make sense. We've got over 5 megs of data coming down. That's a lot of data. The other ones are also 3 megs. That's pretty big. Okay, this is not completely insane, but it gives us some idea of where our data is. So, yeah. So this is where please forget how to switch tabs. Great. Okay, cool. So just to give you guys another shiny slide to look at, things get really interesting, unsurprisingly, when we're able to query across data sources. So Blaze is really handy and convenient as a DSL to talk to one set of data, but if you just put everything in Postgres, I mean, regardless of what the Uber engineering team might say, Postgres can handle it. I'm sorry, I've completely lost my speaker notes, so give me 1 second. There we go. Cool. So whatever the Uber engineering team might say, Postgres can handle it. It can handle all these different kinds of data. You could put them in AWS Redshift. You can put them anywhere that you want. But the idea is that if they were all in one place, you could use SQL Alchemy to get all these results. If they're all in a series of CSV files, you could just use a data frame, right? Why do you need to do that? Well, the thing is that I'm sure everyone here has been in a real-world scenario where for some reason that no one can fathom, all of this data is in several different places and you still need to combine it and ETL it and other such things, and that's terrible. So for lots of reasons, things are in different places. And this is where we find out some of the real power of Blaze, which is going to let us combine our data interestingly. So, combining data sets. You'll notice that I'm basically reading off my notebook notes here. It's largely because I made sure that the notebook was going to be useful for people if they wanted to look at this later on. But we're going to look at a couple of simple queries, right, to try and combine several different data sources in interesting ways and give you an idea of what's possible. I'm not a data scientist, full disclosure, so my queries might not make a lot of sense. They might not be the sort of things that you would actually want to get out of this data. They should give you an idea of what's possible. So, which gender spent the most on books? This combines our users and our transaction data. We take spend by user, which we saw, we got our 5 big spenders earlier. We take that, it turns out we need to do a little bit of data cleaning. Who here has dealt with messy data before? Okay, anyone whose hand is not up, you've either not dealt with data or you're lying. But we need to do a little data cleaning. We need to make sure that we have a string format to join on. We need to make sure that our spend by user and our users have the same columns. And then we say, okay, combine our users with our spend by user derived data set, which is really kind of a Blaze expression that will dynamically be computed when it needs to be. Group them by gender. And let's go. Hooray! So, interesting thing out of this data, which was completely random. But if I were going to try and draw some insights from this, I would be saying, well, look, we actually have slightly fewer men than women on the system, and yet they're outspending the women. So maybe we should be, marketing more heavily towards them or something. Like I said, I'm neither a data scientist nor a marketer, so this is terrible advice. Okay, cool. Let's find out which genre has had the most spent on it. So when I say genre, this is from Project Gutenberg, so this is the Library of Congress classification. It is not the most helpful of classifications. But which genre has had the most money spent on it? So this combines our book data, which is in MongoDB, with our transactions, which is a CSV. So we take our book data, we have a little bit of stuff that we might need to put in later on because Mongo sucks. We have our transactions data, we're filtering out the columns that we're interested in and we want to join on. We join them, and then we use the Library of Congress classification to bucket them up and then see kind of what was spent on what. And I knew this was going to happen. So several layers of traceback later. Several layers. Wow, this is what I have to do. Several layers of traceback later, we discover that okay, so our Mongo query is not present somewhere. This is an extremely unhelpful error. Is one of the cons of Blaze is that when you're using it, sometimes you get these very unhelpful errors. But what that means is basically MongoDB support is not perfect. And when I say not perfect, I mean not that great. So if you know MongoDB and you would like to contribute to Blaze, please come talk to me afterwards. But what we can do, because we have cleverly extracted only the field in our data that we care about, we can just pull that into a data frame. And this is using something called Odo, which we'll talk about later on. But let's do this. We're going to pull all the stuff that we want. And Blaze was able to actually filter out the large set of all the textual data, all the other stuff in our books data set that we don't really care about for the purposes of this query. And here we go. So, surprise, surprise, people are spending the most on literature. They're spending it on English literature, far and away the most. I think that's just an artifact of Project Gutenberg's top 100 books. There's American and Canadian literature, Romance literature, Germanic and Scandinavian literature, Slavic literature, all the way down at, in the 7th, we have philosophy, psychology, and religion. Wow, our bookstore, really caters to fiction readers. Okay, that's cool. So, okay, here's kind of the pièce de résistance of our combined Blaze data queries. In which state have people spent the longest time downloading philosophy books? So this combines our users, our server records, and our books data. It's as many different things as I could conceivably try to pull together. In which state have people spent the longest downloading philosophy books? I don't know if anyone cares, but let's find out. So we have our books data just like before. We need to pull it into a data frame to be able to join it because MongoDB doesn't let you do joins. Well, we have a couple of little helper functions that we're mapping across our data set. And you'll notice that this all looks very much like pandas. It all looks very much like the same sort of NumPy and pandas DSL that you're used to, but it's actually doing relatively larger and more complex queries. And you'll notice as well, and I'm sure you guys have remarked on this, that's a lot of code. That's a lot of code. Well, as I'm sure we all know, dealing with data is messy. Dealing with data often requires complex sort of cleaning operations. And one of the great things about Blaze is you've got this cleaning operation, you've got this filter. Well, it's right here, it's encoded in code. It can be translated to any backend that you want without having to change its shape. So there you go. That's you're encoding your script for your data cleaning process. So we take our books data, we make sure that we've got string IDs to join things on. We take our users data, we take our download logs data, we join them all up appropriately, and then we can do kind of cool things like we've got this like query on the Library of Congress classification column. We can say, okay, where the book is like star philosophy star. So it's a philosophy book-ish. And then we do the math. And it turns out people in Alaska spend a lot of time downloading philosophy. Anyone have any hypotheses as to why that might be?
Dialogue.
Very possible. The next biggest group is people in Wyoming. So, seems to line up. There are all these people in cabins in Yellowstone going, why won't my data download? But the interesting thing about that is that many people can make use of these conclusions. You might think that you have data that isn't particularly amenable to analytics. You might think that it's the sort of data that you don't necessarily need to analyze or query or do things with. And you'll find that when you start to combine all these things, you actually get a lot more insights out of things than you might be expecting. So, for instance, looking at these numbers for Alaska and Wyoming, even like your DevOps people might be like, you know what, we need to open a replicator node in AWS Alaska, right? Because otherwise our customers are getting terrible service. Granted, your DevOps people are not likely to ever want to open a node in Alaska, but it could happen. Cool. So what kind of backends does Blaze support? Well, here is an incomplete list, but this is the list with reasonably good support so far. You'll see CSVs, you'll see HDF5. Who here has actually used HDF5 a lot? If you haven't, it's great. HDF5 is a relatively fast binary storage format which has really good Python support. And it's a column store. It's really good for a lot of your sort of analytic type of data. I've used it a lot as like sort of a temporary store for queries that I'm working on. So Blaze supports that really well. It supports pretty much any SQL database you can think of, because SQL Alchemy is the backend for that. It supports JSON-shaped data. It supports stuff in MongoDB. It supports HTTP URIs. It will transparently traverse that network request. It supports computing across Spark using PySpark and even Spark SQL. And it supports bcalls. Who's used bcalls? Yay, bcalls. Bcalls is great. It's like HDF5, but way less complicated. And way less complicated is good. So you'll see it's by no means comprehensive, but it covers most, if not all, of the data that we frequently look at on a regular basis, right? And adding support for another backend can be relatively easy, and we'll look at an easy example shortly, or it can be a big undertaking, but it's all pretty neatly organized. We're working with Blaze. We've taken the plunge, and my talk was extremely convincing, and you guys have gone, yes, I'm going to use Blaze. So what are the key APIs that you're going to want to deal with? First up is a resource. So a resource, it's simple. It translates a string pointing to data into a Python object pointing to that data. That can be our Postgres query, our Postgres connection string here. It can be a file path. It can be pretty much anything, so long. It can be an HTTP URI. Basically, what that does is it gives us sort of a reference to actually do computations on our data. So, new resource types. You want to create a new resource type? It's really easy. Can you guys actually see this? Thank you. I was a little unsure about that background image. Anyway, so new resource types are easy. You pull in the resource and you say, okay, I want to register this regular expression-ish thing. And if you encounter that, here's how you translate it into a format that Blaze knows how to deal with. So you'll notice that this takes anything, any file path or any HTTP path, which will be transparently dealt with, takes anything that ends with XLS or XLSX, pumps it through Panda's read Excel function, which returns a data frame, and then you can do any kind of computations you want on the data frame. You may think, okay, that's kind of limiting. Data frames don't necessarily work that well across large data sets. Well, XLS files have a limit of 65K rows, so you're not going to have that big a data set anyway, right? But this demonstrates how easy it can be to translate data into a format that Blaze can support. And so you could trivially load and work with Excel data sets if you wanted to. Compute is the next thing that you care about. So in this example, we've got a data set representing some accounts, T, and it has a field balance. And you compute the expression, filtering out people whose balance is less than 0, and you pass the second argument is the actual data set you want to compute against. So the expression is the first part, the data set is the second part, which allows you to divorce sort of the expression that you want to run from the backend you're computing it against. Again, another one of those features where you can take Blaze and sort of use it to query across a variety of different data sets. That's a really critical part of it. Compute does all the work. And data is fun. Data is what you guys have been seeing in all the notebooks, because data is very handy for interactive computing. It basically combines a resource and a compute and allows you to just compute directly on what looks like a resource. And it's extremely handy for interactive exploration, but it loses one of those key benefits that I was talking about, where you can separate the expression that you're using from the backend you're computing it against. Speaking of expressions, that's a lot of different kinds of expressions. They're mostly numerical, as you see. That's because a lot of these numerical rollups are pretty common. It supports a lot of expressions. The documentation doesn't cover all of them, but this is a good start. I honestly recommend, one of the things that Blaze is also kind of lacking in is comprehensive documentation for all this stuff. So I would recommend opening this up in IPython or a Jupyter Notebook and just kind of compute a few things and figure out what data sets that you're interested in, what sort of computations that you can actually run on. Cool. Any questions, comments, or wisecracks so far? Yes?
Go ahead.
Okay.
Sorry.
So you talked about the data size of Excel being limited to component memory. Do the data frames for other sources manage larger data sets?
That's a really good question. So generally speaking, when you translate something into a format Blaze can handle, it really depends on what format you're using there. So Blaze will compute against a data frame, and it can run computations against a pandas data frame. Blaze can also compute against SQL. So when you create something that looks like a Blaze expression and it actually goes against an SQL backend, it's not necessarily pulling that into memory to compute it. It's actually going to construct the SQL query and send that as far back down as it can to the database to compute. So it can handle basically anything that you want. With the Excel files, for example, we deliberately pulled all of that into memory to be able to compute on it. But that's not necessarily the case for every case.
So that was going to be my question, was getting specifically Spark. So would it create a Spark query essentially?
Pretty much, yeah. So when you compute on Spark, it's using the PySpark operations to actually run across your data set.
So it processes on the cluster?
Yeah. Everything's run. So this is basically, if you're familiar with PySpark at all, this is using the PySpark interface. So your query looks exactly the same. It's going to run across your Spark cluster, however PySpark happens to connect. I don't know very much about PySpark myself. All I know is it's a way to get Python to talk to Spark. So I can't tell you details about the efficiency or otherwise, but I've seen it work pretty well.
I'm not sure that people are they compliant. But
yeah.
what I wanted to ask you was, are you looking for additional backend support?
Almost always, yeah. So Blaze, we're going to go into that in a little bit, but yeah, Blaze is fully open source and under permissive license. It would be great to support more backends, because the more types of data you can compute against, the better. And on that note, let's look under the hood. How does Blaze actually do these things? So, fundamentally, a Blaze expression is a symbolic representation of the query, right? So internally, it's a tree of operations. Any of you who are familiar with computer science jargon will recognize this is pretty much an abstract syntax tree right here. And so a Blaze query is a domain-specific language of its own. It's internally represented as this tree of queries. And the great thing about that is that you can transform them. You can store them. You can do whatever you want traversing this tree. And there's a bunch of helpful functions in Blaze to let you do that. So you'll notice that here we've used this really, really simple query. I say query. It's selecting the dollar column from the accounts data set. And that is basically saying, okay, it is a field selection operation, and here's the shape that is computed against, right? So how does this actually compute? So I think this kind of goes to some of the questions that people were asking about. How does this actually compute? Well, step one, it pre-computes all the leaves of the tree that represent data. So this can, for instance, load data into memory if necessary. It optimizes the expression. So this is doing really simple optimizations. It's not a very clever compiler in that sense. It will, remove fields that you're not interested in. Not much more than that. And then it tries to call compute down on the entire expression tree. Okay, so compute down takes the entire chunk of the expression tree and allows us and tries to process it in one go. For instance, distributed processing backends could restructure that tree to parallelize it, and then actually send out the whole chunk of the subtree to different workers to compute. Otherwise, we go up the tree from the leaves. So we take the leaves of our tree, our data sources, all the intermediate nodes or operations that we're combining on them, and we basically go from the leaves and try and call compute up at every stage. So we're doing sort of a slow, progressive combination of all of our leaves of data into our final result. And we just keep doing this until the data type significantly changes. So this is the most common function implemented in Blaze. It encodes most of the logic. So the smallest and simplest unit is, for instance, addition is a compute operation that expects two leaf nodes that contain numbers and or sequences of numbers, and so you combine those two into a result data set there. If the shape of the data we're processing has changed enough, then it's probably worth a re-optimize. So for instance, if we've taken a list of things and we've summed them, so we had a list, now we have a single scalar result, then we might want to re-optimize things, right? And then we go to step 3. So we recurse on this until we actually have our final result, and there's no more leaf nodes to process, and then we call post-compute. Post-compute actually handles the data once the computation has been done. So in the case of any of the SQL stuff, for example, like I was just saying, the computation in question is actually constructing an SQL query. And so once that computation has been done, you have an SQL query, post-compute actually sends that off to the server and collects the results back. So Blaze will, at every point with trying to compute down across the entire expression tree, or by the way that the backends are implemented, will try and push the query as far into the actual backend data store as it can. With an SQL database, this is pretty far. With a data frame, this is pretty far. The data frame will do most of the computation. With, say, a pure Python data structure like a list of dictionaries, not so much. Any questions on this? Because there's a lot to
So is it always grabbing from the data store, and storing in Blaze, basically, the actual whole data set?
It's not, no.
And then,
So
the question really is there any, storage native optimizations?
So yeah, so essentially, all of this depends on the type of the resource that you're working with. So generally speaking, you've got your data resources, and those aren't actually the data sets, right? Those are just pointers to the data sets. And depending on the type of your backend, when you call pre-compute or when you do any of these operations, that may do more or less things. So for instance, when you're computing against an SQL resource, the computation doesn't involve loading any data at all. It's actually just constructing the SQL query. And that gets pushed down all the way to the back end, your Postgres or MySQL or whatever, to optimize it however you want. And then you get the result data. And wherever possible, that's done kind of as at low a level as you can. So if you're combining a pandas data frame with an SQL result set, it'll compute the most of the SQL result set that it can, send that off to the server, and then try and join everything together. So generally speaking, Blaze will not try and use any more memory than it has to. And we'll go into why this is a pain in the ass in a minute. Cool. Yes?
Is it going to send the full result back, or is there a way to tell it, like, hey, I want to iterate over this result?
So by default, it actually returns an iterator over the result set. So however you want to consume it, you can. Cool. Anyone else? No wisecracks even? Come on. So internally, a lot of Blaze is implemented. This is just kind of a nerdy note. Here, internally, a lot of Blaze is implemented as simple functions that handle just one combination of possible inputs. So, like here, we're computing a selection on pure Python data. So this is the selection operation, which is we're filtering stuff out. We get two sequences, one of which is our data, and one of which is kind of a predicate column. So this is a Boolean, do you include this, do you exclude this column? And we just kind of zip them up, and we filter out the ones that have kind of a falsy predicate. And to address kind of both of your questions there, as you see, each one of these here is like it's using ITER, it's making sure that it consumes as little of the data stream as it needs at each step. So the result operation here is going to be an iterator that only consumes the data stream as necessary. And FYI, that dispatch decorator here that we're working with is from a library called Multiple Dispatch, which is really cool for this stuff, and you should check it out. So, computing any arbitrary selection obviously involves much more than just filtering based on some sequences, but this approach allows us to implement one set of operations at a time and gives you a hint as to how different backends are implemented. So, each one of these handler functions that you've got, there's handlers for different data types and different combinations of data types, from SQL alchemy selectables to NumPy ND arrays. And so adding backend support could be as simple as loading everything into a data frame from Excel, or it could be adding handlers for every single one of these expressions that you might be interested in, which is more of an undertaking. So if you were to implement this for, say, Cassandra, you'd be doing a lot more work. Okay, cool. Who likes client server? Wow, such wonderful lukewarm. So basically, like we were saying, the Blaze resource concept combined with a simple REST API gives you Blaze server. The Blaze server allows you to host references to your data and abstract them away. So let's say for any particular reason you have, I don't know, your servers, you have a Blaze server that you want to host on AWS inside your VPC that can talk to your Redshift cluster, for example, without having to store usernames and passwords or anything like that. Basically, it's another layer of abstraction, and you can talk to it using this Blaze ://URL. Right? So the Blaze client acts like any other Blaze resource. It's going to give you the results exactly as you'd expect them, but this is taking advantage of the fact that Blaze queries, Blaze expressions are really expression trees. So it will take that expression tree that you're looking at and it'll actually ship it over to the server to execute, and then stream the results sent back to you. By default, so again, fun nerdy fact, by default the format that's used is message pack for the datasets to be streamed back, but you can configure that however you want. But yeah, so this basically lets you do a lot of really cool things with actually your client server architecture. So you can have, a MacBook that has the Blaze client code on it. You don't need a lot of computational power because your big beefy server is actually holding the Blaze server doing all the math and RAM, or a server with necessary database access tokens or whatever. Yes?
Or you could have, say, your server in AWS with access to databases and resources stored there,
Yep.
and you connect to it without actually having access to those resources,
Yeah,
right?
absolutely. Yeah. So, I mean, you would want to do whatever due diligence is obviously important to give you access to your Blaze server. And Blaze server does not natively implement much of that. In fact, that is one of the things that I'm trying to add a little bit to Blaze server, because the Blaze devs are not really web people. It's not their area of expertise. So it's a thing that I can help with a little bit. But yeah, that's one great use case for it. And it's actually a use case that I'm using at work. Okay, so Blaze is not just Blaze, it's built on top of a lot of libraries, and there's a whole ecosystem of components around it. So we've seen some hints of all of this. We've seen Odo, we've seen some other stuff. So the most independently useful is, in fact, Odo. Does anyone get where this name comes from? Yay! Okay, good. Yes, that's right. The best start. No? A little bit of argument there? There we go. Cool. Yes. So basically this lets your data shapeshift, as you might expect. So for those who didn't get the joke, Odo is a shapeshifter character, and this lets your data shapeshift. It knows how to convert a number of formats directly to each other. So for instance, CSVs to pandas data frames. And it has, where possible, it has optimized stuff. So here, we're looking at loading a CSV, which may be of arbitrary size, into Postgres. And you would think, okay, well, if I tried to load my CSV into pandas and then use pandas.toSQL, this would take hours and hours and hours, and it would be the worst thing in the world. Well, because Odo has specific knowledge of CSV to Postgres, is able to use SQL can use like specific operations, like the copy command in particular for Postgres to actually load that CSV straight into the database as fast as possible. So the cool thing about Odo, and the thing that makes me kind of geek out a little bit, is that it knows how to convert between various nodes, various different types, and it uses this graph of conversions that it knows about to convert between arbitrary data types. So if it doesn't have converting from format A to format B, it probably has format A to format C and format C to format B. So it will actually intelligently use that graph. And some of you guys might have seen in the trace back earlier when we were looking at MongoDB, where it wouldn't compute, you might have seen a function called _Dijkstra. Yeah. So that is Odo. That is Odo trying to convert the Mongo query into a shape that it knew how to compute. And it's using Dijkstra's algorithm to try and find a fast path through that graph. So it's pretty cool. So the other thing that we've seen a little bit and not really understood is data shape. Who here's used data shape? No one. Okay, cool. Well, data shape, surprise, surprise, it describes the shape of your data. Right? So this data shape description here basically says we've got any number of records. Each record has a name field, which is a string, and a balance field, which is a float. This is basically like a type system for your data. It allows Blaze to do optimizations on the kinds of data that it needs to deal with, and do validation that your queries actually make sense and kind of fail fast where that's appropriate. It's also generally very useful, in my opinion, for operating on data with more confidence than kind of the soup of unstructured CSVs that you frequently get. And if you're interested in learning more about this, the Datashape project is a good place to look. There's also a project that kind of backs it called Dind, D-I-N-D, which is a C++ sort of backend library to do a bunch of that powerful computation on the back end. So I've been singing the praises of Blaze, perhaps not in the most convincing of ways, but perhaps in a very convincing way. And obviously it has limitations. I don't want anyone to go away thinking that it can do everything and automatically, magically do all the things that your data has problems with.
Give joins to MongoDB.
Yeah, well, if you use MongoDB, you have other problems, right? But I don't want anyone to get disappointed when it can't do all the things, right? So, what does it not do? What does it not do? That is what it doesn't do. Okay. So, it doesn't clean up your messy data. We noticed that our data, all of our queries, a bunch of them had things like we need to make sure this is a string column, or we need to coerce this to a different data type. It's not going to do the cleaning for you. It will help you with that. It provides a lot of operations that you can use for that, but it's not going to do it for you, right? It also won't support most of the SciPy operations at this point. A lot of those are not implemented. If you would like to implement them, and you know a lot about the SciPy or the scikit-learn operations in question, because of multiple dispatch, you just need to implement kind of the operations you know about, and it will use those where it can. It will not make your existing data handling code magically parallel and super fast. It won't do it, I'm sorry. Blaze fundamentally uses other platforms to do the computation. It pushes things down to a pandas data frame or to SQL, so it's no faster than those, basically. So it's not going to make your queries super optimized and super quick. It's not going to make things access, lots of data in parallel. It will help you with those where possible, but it's not going to magically do things for you. We all saw that. I don't need to explain it. MongoDB support is not great. There's lots of things missing. Personally, I'm not that bothered because, as you may have guessed from my conversation earlier, I don't really like MongoDB. But a lot of people do like it. A lot of people want to use it for analytical stuff, and Blaze attempts to support that. So if you know MongoDB and you're interested in improving MongoDB support, it is super easy. And because of the multiple dispatch tricks that I mentioned just now, because of the fact that we are potentially computing across very, very large data sets, millions and millions of rows, and so we use iterators and generators everywhere, debugging can be kind of a pain in the ass. I mean, who here enjoys debugging Python generators? Yeah, no, you don't. It's okay. I really like Python generators. I think they're the coolest thing in the world, but oh my god, do they suck to debug. And because Blaze is designed around a lot of that iterative computation model, it can sometimes be a pain in the ass to debug. That's it from me. You can contact me on the internet at Necaris. I'm that on Twitter. I'm that on GitHub. You can come to the meetups that I help with. So Saturdays at the public library downtown, come help out, come learn about Python, come help me teach people about Python. Lots of whom have never programmed before. There's a dojo meetup, which I also help to organize, which is every month, where people get together and do cool things with Python. So dcpydojo.org, please do come to that. And if you have any questions or comments or wisecracks left, please throw them out. So one thing I should probably say, Blaze is developed and supported by my employer, Continuum Analytics. It is fully open source. It's under a permissive license. Don't let that stop you. But full disclosure, I feel like, I should say that my employer supports this.
Usually I think about Python 3, but I noticed you had a Python 3 Jupyter notebook. So
Yeah.
Python 3.
Blaze, because of some dependencies, the last version was actually only Python 3.4 compatible, which was terrible. But 0.11, which is I think it's a release candidate, and you can download the RCs from it, but that's 3.5 compatible. So.
Is the only data frame pandas, or does it know about Dask or any of the other alternatives?
So it knows a little bit about Dask. It doesn't know a lot about Dask because Dask is complicated. Dask is also awesome and also supported by Continuum Analytics.
Yeah.
And I would love to talk to people about Dask because I have a lot of possible use cases for it in a project at work, and I would like to be able to work on open source code for money. Yes. Okay, cool. Thanks, everyone.
All right, before we get wrapped up completely,